All right. Section 2.7 from your book is about normal curves. And behind the scenes, or before this, went ahead and gave a little bit of background. At the discretion of your teacher, they could talk about box plots, which talk about range and dispersion, kind of getting your feet wet into dispersion. And then that leads to deviation and how spread out a data set is and what it means to be normal. Okay? And then now I feel like we can talk about these normal curves. Okay? So we will identify when we can apply the empirical rule and call something normal, and we will develop and use the rule for normal curves. Okay? And again, this is all for quantitative data because in order to have a histogram, you have to have numerical measures as your data set. So, a couple of recalls from the last, so also from section 2.7, but from standard deviation. The Z-score. Z-scores measure how many standard deviations data is from the mean average away from the mean average. Okay, that's what a Z-score is. And I also want to give a quick shout out to your book for, they have these every now and again, these how to use your calculator and also how to use Excel to find all of these things. So FYI, in terms of standard deviations and whatnot, that was just on page 246 of your textbook. So I just wanted to, again, make a quick little shout out to your book for giving you some step-by-steps. You could Google it and hope that the person on the other end of the computer is legitimately knows what they're doing. But the Z-score has a formula. So recall that Z is equal to, or you could just ask your teacher because you know that they're legit when it comes to math, is the data, so how the difference between the data value and the average and how many times the standard deviation goes into that difference. So that tells you how many standard deviations a data value is away from the mean. And it tells you if it's above or below, depending on its sign. Where x equals data value, mu equals the mean, and sigma, lowercase sigma, equals the standard deviation. How much is it deviating? All right, let's take a peek at example 1. Who did better? A student in a section of Math 095 where the mean average was a 77, standard deviation of 10. Okay, so that's where student A, they're living in that section. That student scored a 95. Wow, that's really good. Student B scored an 88 on, oh, that's a typo. For Pete's sake. Same, that's supposed to be the same class. Sorry. Math 95 exam in a different section. Okay, so same course but different section where the average was a 75 and the standard deviation was a 5. So right off the bat, I need you to think to yourself, okay, yes, this person scored higher, but also so did everybody else because the average was a 77. This person scored lower, but everybody else scored lower too. So the question is, which student really did better? Because I'm sure we've all experienced the situation where, there are two different students in two different classes, and one has the harder teacher and one has the easy teacher, and you're like, oh my goodness, I wish that I had the easy teacher so that I could feel so great inside and warm and fuzzy. But then you're like, hey, can you use your sense in order to figure out who really did better? Does it really matter what section you're in? Like, did this student, even though they scored an 88, do better or worse than that student who scored a 95? We should be able to tell. So, let's do it. Right. Well, one way we can do this is to maybe look at a number line. So I'm gonna get my purple, my handy purple, and I'm gonna start with this first class. So let's suppose for fun, right, the average was 77 and the standard deviation was 10. Okay, so in either direction, we'll go 87, 97, it would cap out. Let's see, boom, boom, boom. One standard deviation below that would be a 67. Another standard deviation below that would be a 57. The majority of people are got to be between like a 57 and a 97. Okay, so, and this student falls here-ish. Okay, so, and this is the average. The mean average is a 77, and that's where that student is living. Yeah? Now, in the other class, okay, so I'll put the average right here. The average was a 75, and I will put ticky marks for 2 standard deviations above and 2 standard deviations below. Let's see, standard deviation was 5. Okay, so from here to here, this would be an 80. This would be an 85. Below that, so one standard deviation below a 75 is a 70. Another standard deviation below that is a 65. Okay, so here's the average again. And in terms of deviation, this was significantly lower deviation. And that student scored an 88. Well, that's up here. Yeah? That's, so when I look at it just like this, I'm like, oh, that is way better. There's a 13-point spread here, and usually, people only deviate about, on average, about 5 points away from 75. Yeah? Here, there's a 77 plus 10 makes 87. 87 plus 8 makes 95. So 18-point spread. But on average, people are about like 10 over that, which is 87. So when I look at it this way, I'm thinking, oh, this person did better. This 88, this was a tougher exam with a lower average, and everybody scored right around this, 75 marker, because that deviation is low. Whereas here, people scored a 77, but they deviated quite a bit from that. So when I look at this marker being way over here, I'm like, student B did better. Now, a lot of people would just be like, you know what you could have done? Instead of making this kind of a scale, just measure how many deviations were they away. And that's what we have right here for a formula. So this first student in this first 95 class, well, let's see, they scored a 95. The average was a 77. How many times does 10 go into that to count how many deviations were they above the average? Well, let's see. 95 minus 77. That's 18. 18 divided by 10. They were 1.8 standard deviations above the average. Now, the second student in this other class, well, they scored an 88, and the average was a 75. And how many deviations go into that? Well, let's see, 88 take away 75, that's 13. 13 divided by 5, that's 2.6. They were a whole 2.6 standard deviations above the mean. They're way further above the mean in terms of this class than the other student. So, who did better? Student B. Relatively. So, a little bit of a harder test, and they scored a little bit relatively better on it. A graded test without a name on it had a score of 80%. The morning class had a mean of 72 and standard deviation of 3. And the afternoon class had a mean average of 92. Jeez. And a standard deviation of 7. Whoa. That has red flags written all over it too, by the way. Which class is this likely to come from? Explain your answer. Okay, well, here we go. Morning class. We'll go blue style here. Average is 72. So here, let's label it morning. Average of 72, standard deviation of 3. Well, 3 more than that is 75. 3 more than that is 78. 3 less than that is 69. 3 less than that is 66. And this person scored an 80%, where 72 was the mean. Yeah? So there's the morning class. And let's compare that to afternoon. Good afternoon to you. It had a class average mean of 92. Sorry. Okay. I'll get over it. Class average of a 92 and a standard deviation of 7. 7 above that is 99. Can't score above that. Well, I mean, pretty much. 7 below 92 is 85. 87 below 85. 78? Hold on, I have to think. 78 plus 5, right on. I'm sorry, 78 plus 7. So 1, 2, and then 5 more. Yes. 85 plus 7, 5 more, then 2 more. Yeah, okay, good. And this person got an 80. Right there about? Yep. I would say that it's probably more likely that they were in the afternoon class, because that means they were only 1.5-ish away from the average in terms of deviation. I'm sure they're hoping that they were in the morning class, because that means they're pretty much the star student. Like, they are way above average here. But let's do this with a calculation of the z-score. So let's see. So 80, they scored an 80. The average was 72. The standard deviation of that class was 3. So a difference of 8. 8 divided by 3. Oh man, how many times does 3 go into 8? It's like 2 2/3, I would say. 2 2/3. Okay, so if they were in this class, they would be 2 2/3 deviations above average. If they were in the afternoon class, the average was a 92. They scored an 80, and the standard deviation was 7. Let's see. 92 take away 80, that's a difference of 12. 12 divided by 7, I don't think that's nice. Definitely is not nice. 1.7-ish, but below average. 1.7 standard deviations below average. So it's actually more likely that they came from this afternoon class, although they're probably praying and hoping that they came from the other class. Okay. So, which brings us to the empirical rule. Okay? And the empirical rule says this: if a data is bell-shaped, so if the histogram for a data set is bell-shaped, then it is considered normal. And we talked about that in the last section. So if it is bell-shaped, then it's considered normal. And the following applies. Okay, so about 68% of the data values are within 1 standard deviation away from the mean. Okay, so I'm gonna leave myself some room over here to draw the actual bell, but first, about 68% is plus or minus 1 standard deviation from the average. Okay. 2, about 95% is 2 standard, so within 2 standard deviations from the mean. And 3, about 99.7% of the data is within 3 standard deviations from the average. Okay? But this only works if the histogram for the data is bell-shaped and we call it normal. This is what normally happens to bell-shaped data. Okay, so I'm going to draw this out really quick, this bell, and see what we can break it into really quick. Okay. Yep. Very challenging for me to draw symmetrical bell. Okay, so let's say that's my bell. Then that means that the histogram maybe looked something of the sort. Yeah, I'm just rough sketching a histogram that would give us a bell shape. Something like that. Our data maybe looks like that. Okay, so we have this histogram and it looks like a bell, and right down the middle is the mean. So along this scale right here is the mean average, and what this is saying is that if we chop this up into pieces, then let's chop it a little bit. It's wanting us to split it into 3. So I don't know, maybe I'm gonna go 1. I'm trying to make it symmetrical. 1 ticky mark, and then about here, we want symmetry. 1, 2, and 3. Okay, so here's what's going on. It's saying this amount is about 68%. Okay, and if that means that between here and here, within 1 standard deviation around the mean is 68%, then your book says, well, split that in half. This is 34 and 34. Okay, and the mean is right there down the middle. And then it says, all right, fine, that's great and dandy, but if you look between these red bars, then that is 95% of all data values are landing between those. Those are supposed to be symmetric. And that means, normally in class I have my students come up with these, but if you add up 68 plus, 68 plus how much makes 95? Well, 95 take away 68, 27. So 68% plus 27% would give you a grand total of 95, and half of 27 is 13 and a half. Okay, and then they're saying this empirical rule for normalcy is that if you go out 3 standard deviations, well, then you have about almost all of the data. You have 99.7%, if it's normal, living between this value and this value. Okay, whatever those are, depending on the situation with the average and how much your data is deviating. But you have quite a bit there. And that makes this about 2.35%. So that if you add up all of these, you get 99.7% of all the data. What does that leave behind? 0.15 or something? Anyway, yeah. Because 0.3% would be left, and half of that would then be 0.15%. Okay, so now if the histogram for the data set is bell-shaped, then we call it normal, and it satisfies this normally. Okay, so it's called the empirical rule because it just, it empirically happens. It normally happens, which is why all of these names are as such. I do want to show you that your book has beautiful pictures of this. Yeah? Beautiful pictures. And, it's worth looking at and using. But I basically draw this every time I'm dealing with something that is normal or the data set has a bell-shaped. Okay, a couple of remarks before we do a few examples with things that we consider normal. There are many things in life that fit this distribution, which is why it has its name. So namesake here. Many situations fit this normality, okay, or this distribution of looking like a bell. And apparently I had some reference to something in your book, but I really am just going to write down a few references right here. So to name a few things that have normal distribution. So to name a few. Normally distributed data sets. Let's see. The lifetime of batteries. Well, normally the battery lasts about this long. Lifetime of food products. Okay, so it doesn't really die, but you know what I mean, like it expires. So that is a normal distribution. The heights of mammals. height of mammals. All right. So for instance, I don't know, the height of a whale. Take all the whales and measure them, then you would find a normal distribution of heights. Take all the giraffes and measure their heights, and you would find you stack up their frequencies, and they would have this histogram that is pretty normal, shaped like a bell when you draw your histogram of your data. IQ scores. The IQ test has been shown to be biased. Even in its bias, is normally distributed. Weight. Okay, so I say weights just very ambiguous, just like vaguely or arbitrarily, like the weights of, I don't know, people. The weights of 2-year-olds. There, just pick one. Are normally distributed. The lengths of a manufactured part. So like, let's suppose you're on the factory floor and you're making, I don't know, nails. The lengths of those, even when they're machine created, will not be perfect, but the lengths of them will be normally distributed. Okay, so I don't know, a length of a manufactured part. The list goes on, and this is why we call it normal, just because it happens so often and normally. Okay, so I think what we'll do is I'll go ahead and we will apply this to this situation, and then we'll stop our video and restart for the next example. So let's see if we can use this empirical rule. The average age was 15 months with a standard deviation of 3 months in terms of when kiddos start to walk. The data for when children start walking is shaped like a bell. Okay, so that means if it's shaped like a bell, we can call it normal, and the following applies. Got it. Draw a bell curve and label the axis. Okay, here we go. Ugh. My bell does not look perfectly symmetrical, but it is what it is. And right down the middle is the average. The average is 15. So this would be age of kiddo. 15 months old. So age in months. Let's put that there. Standard deviation of 3. So I'm going to go, notice this says plus or minus 3 standard deviations. So I'm going to go 1, 2, 3 standard deviation and 3 below it. 1, 2, 3. Okay. And the standard deviation itself was 3 months. So this would be 18 because that's 3 months more. 3 months more was 21. 3 months more was 24. 2 years old there. 3 months before 15 months old is 12 months old. 3 months before that is 9 months old. 3 months before that is 6 months old. Half a year old. Got it. Okay. It says draw a bell curve and label the horizontal. Done. What percentage of kids walk between the ages of 12 months and 21 months? Okay, I'm going to have to put that up here. So 12 months and 21 months. Well, here's the deal. I know from our picture, from within 1 standard deviation, that was a 34. So I also know there's a missing bar right here. Yeah? Missing bar right there. So this is a 34. This is a 34. And this was a 13.5 in terms of percentages of the data. Okay, so what percentage of kids walk between the ages of 12 months old to 21 months old? Well, 34% plus additional 34% walk between the ages of 15 months old and 18 months old, and then an additional 13.5% walk between the ages of 18 months old and 21 months old. 68 plus 13.5. I am fairly calculator dependent here. All right, so what percentage of kids walk between the ages of 1 year to just before 2 years old, 12 months old to 21 months old? About 81.5% of them walk between those ages. What percent of kids walk after the age of 21 months old? Oh, so I'm looking up here because that's where they're older. Well, up here, so if I go, so this is 1 standard deviation away, 2 standard deviations away, then it looks like we have 2.35% between 2 to 3 standard deviations and 0.15% older than that. So what percent of kids walk after they are 21 months old? Well, 2.35% plus 0.15% is 2.5% of them walk after they are 21 months old, which is why they say if your 2-year-old hasn't started walking, there could be a problem. Maybe there's an underlying cause for why they aren't walking yet. Like hypotonia, which is something that one of my kids has. Low muscle tone is what that's called. Anyway, what is the probability that a kid will walk before they are 12 months old? Okay, back to the curve, because I need this curve. This curve helps me so much. Okay, I'm drawing in my bars, and I might as well label everything. I've gotten to the point where I guess I'm just going to label everything. Next to the 34% was a 13.5%, then a 2.35%, and then down here a 0.15%. Okay, so this curve is super duper handy. We are looking for what is the probability that a kid will walk before they are 12 months old? Okay, so before 12, that's 12 months old or younger. That's over here. Okay, all of this. All right, well, we're just going to write that as a percentage again. So we have 13.5%, 2.35, and 0.15%. Okay. 13.5% plus 2.35% plus 0.15%. So this is 2.5. 3 plus 2 makes 5. 5 plus, okay, so this is 16%. They are 16% likely to walk before they are 12 months old. So when it says probability, that's still just a percentage, and they are 16% likely to walk before they're a year old. If there are 1,500 kids in a village, about how many of them start walking after the age of 21 months old? Well, here's the thing. We found out in number 3 that about 2.5% of kids walk when they're 21 months old or older. So that's this, right? We need to take 2.5% of the, so 2.5% of the 1,500 kiddos. Okay, back at it. 2.5 hundredths of 1500. Handy calculator. Oopsie. I definitely put it in wrong. That's all right. Is about, okay, so I'm going to write this down, which feels awkward. So how many kids? Yeah, about 37 and a half kids start walking after 21 months old. I don't know. Whatever you want to do, round down to the whole child or round up to the whole child. I'm indifferent. Let's just write about 38 of them. After they are 21 months old. There you go. There you have it. So in the rest of the notes, we're going to see this happen in a couple of different other scenarios, and so that we can either see a pattern of how we solve these problems that are normally distributed, or if we're like, okay, how do we approach each one of these problems?